Welcome to this explainer. Today, we're diving into the UVM driver. It's basically the heroic component, the great translator of the hardware verification world. Think about the fundamental problem we all face as verification engineers, right? We write these highly abstract, object-oriented test sequences. But our devices under test, our DUTs, they don't speak object-oriented. They only understand raw voltage, just ones and zeros toggling on physical pins. So how exactly do we bridge that massive gap between high-level software and rigid hardware? Well, the answer is the UVM driver.
Here is our roadmap for today. We'll hit the hardware translator, the communication bridge, the pull handshake, how we go from transaction to DUT signals, and we'll wrap up with implementation and debugging.
Let's jump right into Section 1, the hardware translator, and really define its role. So, the UVM driver. It's a highly specialized, completely active piece of verification IP. Now, it doesn't generate your test data, and it definitely doesn't check the results. Instead, it really just has this one absolutely critical job. It actively pulls transaction-level items straight from a sequencer and literally translates those abstract properties into pin-level, cycle-accurate signals right on the DUT interface. It's honestly like a bridge between two totally distinct worlds. On one side, you've got your abstract sequence items, variables for things like read address or write data. But on the other side, it's just raw, rigid pin activity. The driver's the thing taking that nice, flexible read address and executing it as a rigid, perfectly timed protocol, literally cycle by cycle.
Moving on to Section 2, the communication bridge, and specifically TLM ports.
Okay, so for the driver to translate data, it obviously needs a way to receive it first, right? In the UVM architecture, the sequencer is the arbiter holding all those generated transactions. But here's the kicker. Data isn't just pushed blindly into the driver. The sequencer and driver are connected through specialized transaction-level modeling, or TLM, interfaces. And these are built specifically for a really unique pull execution semantic. If we look under the hood, the driver is actually a parameterized class that extends the core component type. It uses two key parameters, REQ for the request item and RSP for the response. And this parameterization, it's absolutely crucial. It is exactly how the driver knows what kind of abstract object it's going to be pulling from the sequencer.
So the most important mechanic here is that pull concept we mentioned. Operating through its seek item port, the driver is never force-fed data. Instead, it actively asks for the next item off the assembly line. And because it's completely bound by the actual physical timing of the hardware, the driver dictates the entire pace. It only pulls new transactions when the physical hardware is genuinely ready for them.
Which brings us to Section 3, the pull handshake, seeing this protocol in action.
This dynamic handshake is basically a continuous, repetitive loop running inside the driver's time-consuming run phase, and it follows a really strict four-step sequence. Ask for an item, wait for the sequencer to arbitrate, execute that physical translation to the pins, and finally, report back that the job is done.
Now, Step 1 relies heavily on the get_next_item method. When the driver calls this on its seek_item_port, it literally halts its own thread. It blocks the simulation execution, just patiently waiting until the sequencer arbitrates and delivers that next transaction. Once that method returns, boom, the driver has the randomized request in hand, ready to rock.
Then, once those physical signals are perfectly driven out onto the interface, the driver absolutely has to call item_done. This is what concludes the cycle. It signals the sequencer to go ahead and remove that item from its internal FIFO. And, a cool little feature, you can actually pass a response object back through this method if your sequence happens to need to know the outcome of the transaction.
All right, Section 4, transaction to DUT signals. Let's look at the actual execution flow.
Let's trace the complete life cycle of one of these transactions. Picture this. At 0 nanoseconds, a sequence generates our abstract item. Then, say at 10 nanoseconds, the ready driver pulls it in via that handshake we just talked about. By 20 nanoseconds, the driver's custom logic is translating those variables into discrete steps. And finally, at 30 nanoseconds, those steps physically toggle the interface pins. It's pretty amazing. The abstract has successfully become physical reality.
And that brings us to our final section, Section 5, implementation and debugging. Let's bring all this together. To finalize your implementation, the driver and sequencer literally have to be wired together. During your agent's connect phase, it's just this single vital line of code that connects the driver's seek_item port straight to the sequencer's seek_item export. And believe me, you don't want to forget this. Without this physical TLM connection, the second you call get_next_item, you are going to get hit with an instant fatal null pointer exception. Not fun.
Now what happens when things inevitably go wrong and your waveforms look like total garbage? Well, that's when you rely on the UVM reporting mechanism. By strategically dropping UVM_info and UVM_error macros inside your translation logic, you can print out the sequence item's contents right before it hits the physical pins. Then, just by adjusting your command line verbosity, you can isolate exactly where that translation failed.
But wait, what if your driver is coded perfectly, but the simulation just mysteriously ends before any pins even toggle? You've got to remember, driving hardware takes actual physical time. If your sequence forgets to raise an objection, or say your driver takes a bit too long responding to a hardware delay, UVM is going to look around, see no active tasks, and just instantly exit your simulation at 0 nanoseconds. So keep an eye on those objections.
Before we wrap up, I want to leave you with a final thought. The driver is really only one half of the UVM agent, right? It's perfectly translating your code out to the hardware pins. But verification? It's a closed loop. If the driver is basically shouting into the hardware, how are you going to architect your monitor, that passive observer on the other side, to perfectly translate those physical pins back into abstract code? Because that's the only way to ensure your scoreboard gets the whole truth. That, my friends, is the next great challenge in your UVM journey.